In a stunning leap forward for artificial intelligence, Google's AdaTape has emerged as a groundbreaking force, leaving the tech world austere with its 99.9% accuracy. With its unprecedented precision, AdaTape sets an electrifying new benchmark, heralding a fresh era in AI capabilities. Step into the future with us as we unpack the awe-inspiring implications of this newfound AI standard that is poised to reshape industries and redefine possibilities. While humans can adapt their thinking and responses based on varying situations or conditions, neural networks, though incredibly potent and intricately designed, are constrained by fixed functions and inputs. They consistently execute the same function regardless of the nature or intricacy of the presented samples. The researchers employ adaptivity, a potent paradigm that not only gives practitioners freedom regarding the downstream use of these models, but may also operate as a potent inductive bias for resolving some difficult classes of problems to overcome this issue. It refers to a machine learning system's capacity to modify its behavior in response to a scenario or environment change. Understanding the nuances of traditional neural networks, which have been the pillars of machine learning (ML) for years, is like comprehending our set pathways or habits. With their fixed functions and input methods, these traditional models can only sometimes adjust according to the ever-complex variables and dynamics of the real world. The need for adaptivity has become a foundational requirement in modern machine learning, paving the way for revolutionary concepts such as adaptive computation. Reorientating our focus on this particular aspect, we now invite you to delve into Google's latest introduction, the AdaTape Model. AdaTape uses a tape bank to store all the candidate tape tokens that interact with the model through the adaptive tape reading mechanism to make a dynamic selection of a variable size sequence of tape tokens. The researchers use two different methods for creating the tape bank. An input-driven bank. The input-driven bank extracts a bank of tokens from the input, which employs a different approach than the original model tokenizer for mapping the raw input to a sequence of input tokens, and a learnable bank of more general method for generating the tape bank by using a set of trainable vectors as tape tokens. After this, the tape tokens are appended with the original input and sent to the transformer. Then, the two feed-forward networks are used. One is used for the original input and the other for all tape tokens. The researchers observed slightly better quality using separate feed-forward input and tape token networks. Adaptive computation is an approach where the model's computation capacity adjusts itself based on the complexity of input data. By breeding models with such adaptivity, we can construct an efficient and agile design more attuned to the dynamic nature of data sets. The AdaTape model by Google brings this capability into the limelight, standing out with its simple implementation process and accuracy. A significant hallmark of this model is its technique to infuse adaptivity into the input sequence, rather than diving into the model depth. This innovative approach unlocks expansive possibilities, especially in neural networks. So, how does AdaTape make this possible? Well, the model operates with an adaptive tape reading mechanism, responsible for determining the number of tape tokens to be added to each input, based on its complexity. This process relies on a transformer-based architecture that uses adaptive functions and vector representation. Peeling another layer of the AdaTape model, we encounter the tape bank concept. It is not as complex as it sounds. It acts like a storehouse or reservoir, where all the candidate tape tokens are collected. This tape bank can be generated through an input-driven bank and a learnable bank. Once the tape tokens have been selected from the reservoir, they are merged with the original input. The transformer then processes this combined data. The fundamental role of the feed-forward networks comes into play in this stage to ensure maximum efficiency. Adaptive computation refers to the ability of a machine learning system to adjust to its behavior in response to changes in the environment. While conventional neural networks have a fixed function and computation capacity, i.e., they spent the same number of flops for processing different inputs, a model with adaptive and dynamic computation modulates the computational budget it dedicates to processing each input, depending on the complexity of the input. Adaptive computation in neural networks is appealing for two key reasons. First, the mechanism introducing adaptivity provides an inductive bias that can play a key role in solving challenging tasks. For instance, enabling different numbers of computational steps for different inputs can be crucial in solving arithmetic problems that require modeling hierarchies of different depths. Second, it allows practitioners to tune the cost of inference through greater flexibility offered by dynamic computation, as these models can be adjusted to spend more flops processing a new input. Neural networks can be made adaptive by using different functions or computation budgets for various inputs. A deep neural network can be thought of as a function that outputs a result based on both the input and its parameters. To implement adaptive function types, a subset of parameters are selectively activated based on the input, a process called conditional computation. Adaptivity based on the function type has been explored in studies on mixture of experts, where the sparsely activated parameters for each input sample are determined through routing. While conventional neural networks have a fixed function and computation capacity, a model with adaptive and dynamic computation modulates the computational budget it dedicates to processing each input, depending on the complexity of the input. Adaptive computation in neural networks is appealing for two reasons. One, they provide an inductive bias that enables different numbers of computational steps for different inputs, which can be crucial in solving arithmetic problems requiring modeling hierarchies of different depths. Second, it facilitates the ability to tune the cost of inference through greater flexibility offered by dynamic computation, as these models can be adjusted to spend more flops processing a new input. Consequently, the researchers of Google have introduced a new model that utilizes adaptive computation called AdaTape. AdaTape is very simple to implement, as it directly injects adaptivity into the input sequence instead of the model depth, and it's also very accurate. AdaTape uses an adaptive tape reading mechanism to determine various tape tokens added to each input based on the input's complexity. AdaTape is a transformer-based architecture that uses a dynamic set of tokens to create an elastic input sequence. AdaTape uses the adaptive function. Also, it uses a vector representation to represent each input to dynamically select a variable-sized sequence of tape tokens. The researchers tested the utility of AdaTape on many parameters. They found that it outperforms all baselines, incorporating recurrence within its input selection mechanism, providing an inductive bias that enables the implicit counter maintenance, which is impossible in standard transformers. The researchers also evaluated AdaTape on image classification tasks. They tested AdaTape on ImageNet 1K and found it in terms of quality and cost trade-off. AdaTape performs much better than the alternative AdaTape transformer baselines. In conclusion, the AdaTape model by Google suggests a promising future in machine learning and neural networks. Introducing adaptive computation into neural networks unfolds a new dimension of progress. This innovation can potentially unleash unparalleled efficiency and accuracy in model computation. As the tape of developments in ML continues to unfurl, adaptive computation is no doubt going to play a key role. The flexibility and adaptiveness of such models signals a game-changing direction in how neural networks will function, adapt, and evolve in the coming years. What are your thoughts on this? Let us know in the comment section below. If you liked today's video, then leave a thumbs up, and do not forget to subscribe to the channel. See you again soon in another video.